So I'm Filippo. I now work at Google on the Go team, but this research was from before I joined the company. And it was done in collaboration with Sean Devlin, who you might know as the author of the recent CryptoPulse, the cryptographic challenges once known as the Matasano crypto challenges. So the story of this talk starts when a Cloudflare engineer found something weird verifying certificates in a CT log. It found a certificate with a signature that wouldn't verify. And that's weird because CT logs verify signatures before accepting certificates. So something had to be up with the code that was being used to verify them. It turned out that the bug was a specific bug in the implementation of the NIST P-256 elliptic curve. And more specifically, in the x86-64 assembly implementation. This was optimized implementation written by hand in assembly to make these operations on this elliptic curve especially fast on the architecture which is the most popular one on computers that are not mobile or embedded these days. So Cloudflare reports this vulnerability to the Go team, and Adam Langley on the Go team comments that yes, that's a problem, although it's not obvious if someone will be able to squeeze something out of this hole. But you know, it would be a cool paper. So yeah. Sean and I met in Paris to look at this vulnerability. That's nothing else than a challenge right there. And 1 month later, we figured out a way to mount a complete key recovery attack against real protocols as implemented by real implementations that would recover the entire private key from that small, extremely rare bug in the implementation. Go releases were minted with the fix, and of course we're talking about something that does not apply to the current Go distribution. So first of all, I want you to understand a bit of what the code was doing. Now, elliptic curve implementations have as their bedrock field arithmetic implementations. Those are nothing else than operations done modulo a prime p. This prime p is fixed for each elliptic curve. So for example, the value p here would be a constant for the NIST P-256 curve. And a lot of the operations you need to do to build the wider implementation will have to be modulo this p number. For example, the code we're going to be looking at today is the code to subtract two numbers modulo p. Straightforward enough. You have A and B and you want A minus B. That's it. That's what this code does. Why is this hard? Well, P is a 256-bit wide number. There are no registers in your machines that can hold a 256-bit wide number. So instead, you have to break it up over multiple registers. You actually know how to do this. Every time you do columnar subtraction, you are using very small registers 1 digit wide, and doing subtraction between the two digits, and then doing a borrow from the next digit, right? This does the exact same thing. It breaks up the 256-bit number into 4 64-bit registers, then subtracts them one by one, and if there's a borrow bit, it borrows a 1 from the next more significant register. So that's what you're looking at for the very top block. You look at a sub-Q instruction, which is just set A to A minus B. And then afterwards, SBBQ instruction, which means the same thing, subtraction, but with the borrow. So if the previous instruction had to borrow a bit, the carry flag in the CPU is going to be set, and the next instruction will remove 1 from the result of the next operation. You do that multiple times, and eventually you end up with just the final borrow that tells you if you underflowed or not. So this function is longer than just that block. Why? Well, this function is doing 2 additional things. This function is, of course, handling the case where you have to be doing the subtraction modulo p, not modulo 2 to the 256. And it's handling the fact that you want that to be in constant time. If this function took a different time based on whether or not, for example, there was an underflow or an overflow, that would leak information to an attacker, like us, and we would find out things about the key, like we did, but for different reasons. So instead, what does it do? Pretty simple. It starts by doing the subtraction, a minus equal b. Then it saves that value of a in a separate set of registers. And then it adds to a p. Why? The problem is that a minus b might have underflowed. And it wraps around at 2 to the 256 because that's how wide 4 registers are. But that's not correct. You want to wrap around at p, not at 2 to the 256. So instead, what it does is that it adds back p. P overflows, so one underflow and one overflow bring it back into the right space, correct the error. And since adding p for an operation modulo p is not a problem in arithmetic terms, the result is correct. And finally, the last block has to decide, which one am I going to use? The one with the p added or the one without the p? If adding p had, if subtracting b did not underflow, then you can just use a minus b. But if instead it had underflowed, you have to add p. You can't always use the one where p was added because that would have overflowed in the other case. So that's what you're looking at with that mul0 register. The borrow bit from the first chain, from a minus b, is saved in a register so that we can use it later to make a decision. And that will tell us if a minus b underflowed or not. And based on that, it makes a decision with some CMOV instructions. CMOV instructions just, in constant time, copy a value from left to right in this notation based on what the zero flag is. And finally, there is essentially dummy operation, in theory, that just checks mul0 and uses it to set the zero flag. Where's the bug? The bug is that dummy operation right there was supposed to be something like add 0 or end 1, something that doesn't actually change mul0, but just operates on it so that the zero flag gets set based on what mul0 was, so that then we can use it to make the decision in CMOV. But it's not. That's add with carry. There's a C in there. So that 1 byte mistake makes it take in the carry bit from the previous instruction. What's the previous instruction? It's just the end of adding p to a minus b, which has nothing to do with the decision that mul0 is there for. So this is sneaking in a carry that has nothing to do with what we're trying to do. And that influences the decision. Now, this would be wrong most of the times, but instead the CMOV instruction is swapped. Instead of being if 0, it's if not 0. So 2 mistakes cancel each other out, and most of the times everything goes well. And that's why it escaped testing. So almost always, this is not a problem. Except that there is a difference between the old code and the patched one. And the difference is what happens when that carry bit is not there. A rare occurrence, but sometimes adding p does not overflow. And if adding p does not overflow, the carry flag is not set, and the result is wrong. Instead of returning a minus b as it should, it will return a minus b plus p, which will end up being higher than p. A specific case of this is that if you try subtracting 1 from 1, 1 minus 1, it will return p instead of 0, because adding p will not wrap around. So why is this a problem? Well, this is a problem because once in 2 to the 32 times, that result will be wrong. And when that happens, something will break higher up. But this is rare, again, 2 to the 32 times. That's why it went completely unnoticed until it made a signature not verified that someone was really, really sure that should really verify. So this is the bug. Now, we didn't find this bug. We worked on how to use this bug, which is a carry propagation bug, to mount an attack to actually recover something useful, the key. Now, you might be asking, how does forgetting to carry the 1 or carry a 1 that wasn't there, very literally forgetting to carry the 1, cause a full key recovery attack? Now, that's exactly what this talk is about, but to understand that, I need you to take you back for a moment and do a crash course on elliptic curve cryptography. Sounds scary. I promise I've done it before and people survived. Now, we know that there are fields, right? We know that there are operations are done modulo P, because that's what we're looking at. And that's what all numbers we work with are at the lowest level. Numbers modulo P in the field. Then there are points. Points are simply x and y coordinates, where x and y fit in an equation, which is the curve equation. We don't care about the curve equation. Don't worry, it's not even on the slides. Because what we're going to be working on is the abstraction above that. The abstraction critical to understand this attack is the group. A group is two things, a generator point and an operation, addition. What's this special about the generator point? If you take the generator point and you add it to itself using that addition you defined, a certain number of times, you go back to G. That number of times is called the order of the group, and it's another very big number in the order of P and 2 to the 256. So it's a 256-bit wide number. But this is important, it's a cyclic group. So you can keep adding G, and you hit a bunch of points in the group, and eventually you wrap around and you're back at G. This is a group. If you give a group to a cryptographer, they will build the Diffie-Hellman on it. So to build Diffie-Hellman, you need multiplication. But we only have addition. Now, if you know how to do addition, you know how to do multiplication. If you want to multiply by 5, you add. And there's no special definition of multiplication in groups. It's just repeated addition. And addition and multiplication follow all the rules that you already know about. They are commutative and they're associative. So, you know, you can do first add 5 and then add 7, or the other way around. You can group them however you like. Then, as I said, you give us a group, we build Diffie-Hellman. You might already know Diffie-Hellman from its finite field version, but if you don't, it's not a problem. Here's how it works on elliptic curves. The private key in Diffie-Hellman is a giant number, modulo the order of the curve. It has no special properties except it's this giant integer that you select at random from a cryptographically secure random number generator, hopefully. Then you want to generate a public key for your site. How you do that is that you just multiply this giant number by the generator point of the curve. So generator times the giant number is your public key. You send your public key to your peer generates a private key and sends their public key to you. And then to generate a shared secret between the two of us, that's the goal of Diffie-Hellman, we take the public key of the other side and multiply it by our private key. So the final result on our side is generator times the other party's private key times our private key. They do the same, and on the other side it's going to be generator times our private key times their private key. Multiplication is associative, it's commutative, these two results are identical. So since we have identical results, we can do Diffie-Hellman, and then we can use that shared secret, for example, as a session key, or as an encryption key in a public key encryption scheme. So this is how to build Diffie-Hellman from the group. But I glossed over something. I told you that how we do multiplication is by adding and adding and adding and adding and adding. And then I told you that we take a giant number and we multiply by that giant number. Of course, you can't add G to itself 2 to the 255 plus whatever times. There is literally not enough energy in the universe to do something 2 to the 255 times. And I'm not making this up. I wanted to go into the physics and then regretted it, and so we're moving on. But What I can tell you is how to avoid that problem and what to use to actually multiply by this giant number. We use what's called a double and add algorithm. Now, we take our giant D, and we consider it as a string of bits. There will be a most significant bit on the left, because big endian is the only reasonable way to work, and then all the way to the least significant bit on the right. The most significant bit is worth 2 to the 255, then 2 to the 254, etc., etc. What we do is that we do a sequence of operations, that's the double and add algorithm, based on the bits of the key. We want to generate the product Q times D, okay? So we start from the most significant bit. If it's set, if it's 1, we add Q, and since there's nothing, we just take Q for now. Then every time we move down 1, we double. We double the running result we have. We add a double operation to our chain. Now, what happens by the time we are at the end to this Q that we added now? It gets doubled 255 times. So it gets to have exactly the value it was supposed to have for its significance, which was 2 to the 255, because it's the most significant, most important, highest valued bit in the key. Now, this might not be immediately intuitive, but we're going to run through it. So we move down 1, and we do a double operation. At the bottom there, I'm keeping a track of the operations we have to do on our running product. Then we check the bit, and it's 0, so we don't add anything. We double again to move down 1. This bit is 1, so now we add Q. And then we move down by doubling. This bit is 1, so we add Q, and then we move down by doubling. We keep doing that, skipping the 0 bits, and adding 1 for each 1 bit. So what we get at the end is this string at the bottom of operations that if we do them in that order with the Q point that we want to multiply, the final result is D times Q. Now, this might have clicked. If it didn't click, the part that you need to understand for the attack is that given a private key, we generate a sequence of operations that we do on the point, and we use that as the result. Okay? So you're given a point and a number to multiply, and based on the bits of the point, which is our private key, we build a custom, very specific to the key sequence of operations. And the operations are the same up to if the first bits are the same, or if all the bits are the same. If a bit is different at position 100, all the operations before that are going to be the same. So we're going to use this fact, the fact that a key bit string maps directly into operations done to the point to build our adaptive attack. So back to our carry bug. We have a bug where a wrong result is returned from a very internal function. It even has internal in the name. So what does it actually break? We look at the code, and it's called by point add, adding two points together, and it's also called by point double, which is just an optimized way of adding the point to itself. And that is used in scalar multiplication. Scalar multiplication is exactly what I just described. It's a fancy way of calling multiply by a sequence of addings. So you know how to do scalar multiplication. Now, how is this used in a real protocol? Well, this, for example, in elliptic curve Diffie-Hellman is used with a point which comes from your peer, because that's the public key of the other party. A scalar, which is the giant bit string, which is your secret key that the attacker doesn't know. And the result is the shared secret. The shared secret is going to be what's used, for example, to encrypt this connection we're setting up or to decrypt this message we are receiving. Now, this is used, one way to use this is normal ephemeral Diffie-Hellman, where each part generates a new private key at every run, and we can't attack that. But there's another way of using Diffie-Hellman if you feel brave. And it's by fixing the private key on one side. That's useful because the public key also never changes. So you can, broadcasted, you can put it in a certificate, you can deploy it to machines, print it on business cards. And I'm not joking, that's what happens if you try to use it with PGP. So the point is that the private key, the scalar right there, that never changes on our side. While the public key is different every time we do this with a new peer, which might be an attacker. So recapping, scalar multiplication is called with an attacker provided point, a secret private key, scalar, and the result, the shared secret, is going to be used to do some interaction with the attacker. Now, what can the attacker learn from this? It learns whether the bug triggered or not. Because if that function at the bottom doesn't work, the shared secret, the result, is going to be wrong. And if that's wrong, the TLS connection, for example, will break and it will terminate. And that's what in cryptography we call an oracle. An oracle is something that has some information hidden inside it that we want to discover, but that we can't see directly. But we'll answer questions of some sort about this thing. The question we can ask to this one is, if I give you this point, do you calculate the result correctly or not? Now, once we box this into this kind of oracle, that's game over. Because if you give an oracle to a cryptographer, they will build an adaptive attack. Let's see how. So let's say that we have two magic points. Okay? One of them breaks if you add it, double it, add it, double it, add it, double it, and add it. And it breaks at that last addition. And from there on, everything is broken. Another magic point breaks if you add it, double it, add it, double it, add it, double it, and it breaks specifically on that double operation. Now, how do we use this to discover a bit of the key? Let's say we already know the first four bits of the key. Based on what the last bit of the key, the fifth bit of the key is, the operations will follow one chain or the other. So they will hit the bug on, it will hit the bug only on one of the 2 points based on what the bit of the key is. So we send both points to our oracle. One of them causes the bug and breaks the connection. One of them doesn't cause the bug and doesn't break the connection. What does that mean? That the one that broke the connection is the one that corresponds to the bit of the key. And we learned a bit of the key. Now, if we learn a bit of the key, it's usually over. Specifically, it's over if we learn a bit of the key, and then we have a way to discover the next bit, given all the previous ones. And how do we proceed on this attack? Well, once we know the first 5 bits, because we just figured them out with these 2 points, we generate 2 new magic points that crash on the 2 different paths of the next bit. And we send them both. One of them breaks, one of them doesn't. We learned another bit. We generate 2 magic points. We send them both. And we keep doing this until we have your key. Now, what's this called is an adaptive attack. And it's adaptive because we can't generate the 2 magic points to find bit 6 unless we know bit 5. And that also means that we can pre-compute points for all the possible chains because there are as many chains as there are keys. But we can generate points for the 2 possible chains for the next bit that we don't know, given all the previous ones. Now, we are extremely proud that we had figured out this attack. If anyone in the room is in the academic career, they will know the feeling then of going to the literature and finding that Billy Bob Brumley figured this out in 2011 before us. So the attack is pretty much the same thing. Although this was against a 2006 bug, 2007 possibly, and it was published in 2011. So there was a bit of consolation in the fact that it took a few years to notice that that bug was exploitable, so we're still pretty happy. But the paper is eerily similar. There is a bug, it's not the same, it's not in the same function as I've shown you, but there is a bug in OpenSSL. It does the exact same thing. It breaks, and you can generate 2 magic points that break based on the 2 bits, and you can send them both and build the same adaptive attack. Now, it's exactly the same, except that it's absolutely not the same in terms of implementation. And that's because the Go implementation was using certain optimizations based on the work by Krasnov and Guaron that they applied in the meantime to OpenSSL too, which speeds up that double and add sequence by a lot. Instead of looking bit by bit, one bit, add a point, double, maybe add a point, double, maybe add a point, double. Instead, it looks at chunks of 5 bits in a specific encoding based on the Booth algorithm, which is from the 50s. Not kidding, not wrong, paper from the 50s. Still speeding up things. But at the end of the day, what it's doing is that it takes windows of 5 bits, and for each window, the value can be from -16 to +16. And instead of adding 1 and then doubling, it will add or subtract 1 to 16, and then double 5 times to catch up, to move down. So it starts by making a precomputation table, and once it has the precomputation table, it will use it to double 5 times, and then look at the window of 5 bits, add or subtract 1 to 16 from the running result, and double 5 times again until the windows have run through the entire number. So, as I said, this is Booth encoded, so it's a little different than that. So instead of talking about 5-bit windows, we talk about limbs. Limbs are nothing else than each sign bit and 1 to 16. So the value you want to add or subtract, 0 to 16, and whether you want to add it or subtract it. And that's a sequence of values that we apply to come to our product. But then the attack pretty much rolls off the same way. Instead of attacking the two options, add or not add, we attack each possible value that you're adding from the precomputation table. So now for each limb, there are 33 values, because plus and minus 0 are not distinguishable. And we generate points for, on average, half of them, which happens to be 16 because there's some overlap. And so on average, we take 16 points instead of 16 points to figure out 5 bits of the key instead of 5 to figure out 5 bits of the key. So it's approximately 3 times slower, but it works the exact same way. Now, as I said, it works the same way. So we're targeting things that will cause the bug to trigger either in adding the limb from the precomputation table, specifically that limb from the precomputation table. So we'll have a point that only breaks when you add 13, and one that only breaks when you subtract 12. And we send each of them, and one of them will break, and we will know that limb. Or break in the 5 doubles that come immediately after, which still depend on the previous limb. Now, the one thing I didn't tell you is, okay, but these magic points, where are you pulling them out of? And the answer is that we don't have an algebraic way to figure them out, partially because by the time they reach that point of the chain, a lot of things have happened to the value. But we have, and it would be hard to undo them. But so instead, we just took the extremely fast implementation of the curve and added an assembly hook to just tell us whether or not the bug would trigger. And then we run a fuzzer. So that would just raise a flag, set a register, if the conditions for the bug were met. So it would notify us instead of breaking. And then we wrote a small scaffolding around that, which would execute all the operations that we already know from the previous limbs, all the operations that we've already learned, that we know are going to be executed. And then for each of the possible next operations, so subtract 16, subtract 15, all the way to add 15, add 16, we look for something that breaks for only one of these operations. If we find it, that's it. That's a candidate point. We send it to the oracle, and we check if we were lucky. We removed some of the constant time stuff because that code had to be constant time. Our doesn't have to. And turns out that the branches are a little faster. So this was generating point at a very acceptable rate. Of course, to generate points, we need test points, candidate points that we can try and figure out if they are going to be useful points or not. So instead, what we did there is that we just started from a random number, multiplied it by g, and that was a pair, and then just kept adding 1 to the private key and g to the public key. Remember that the private key is just the thing we're going to multiply G by. So if you add 1 to the private key and G to the public key, you have a new pair of valid points, point and private key. Why do we need the private key? Because the only way we can ask the oracle, does this point cause a bug, is by checking if the whole protocol works correctly. If we don't know our private key, there is no way we're going to know if the other side made a mistake. So this worked out. We had magic points for all the different values we wanted. We added some post-processing because there were plenty of false positives. But eventually we had a steady stream of points that would only break at that specific point for that specific operation. So we know how to proceed in the attack once we know a few limbs. We know how to find the n+1 limb if we know the nth limb. Now the question is, how do we start? How do we find the first limb, the first 2 limbs? You could think, you do the same thing, right? You generate a point that only breaks when you take 3 from the precomputation table, because that's the first limb, and you multiply it, you double it 5 times. And you do that, you generate it, you try it, and what happens is that it also breaks for 6 and for 12. Why? Well, 6 in the precomputation table is nothing else than 3 doubled. So if you find a point that breaks when you take 3 and you double, 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 double. That will also break when you take 6, which is nothing else than 3 double, and then you double, 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 double. So it's going to break sooner, but we don't have visibility into when it breaks. We only get to know it worked, it didn't work. And it will break also for 12, because 12 is again 3 double, double. So it will break after you do double, double, double. So how do you fix this? You generate 3 points. You generate one that breaks doubling 5 times, one that breaks doubling 6 times, and one that breaks doubling 7 times. You send all 3, and you look at which ones break. If they all 3 break, it's 12. If only 2 of them break, it's 6. If only 1 breaks, it's 3. It's even harder than this because the next thing might be 0 and more doubles might happen, but that gets less and less likely the more zeros you string. So I'm not suggesting adding zeros at the top of your private key to defend against this attack. But eventually you come to a pretty certain about the first limbs. And the good thing is that you can pre-compute these. These don't depend on anything, don't require you to adapt on any previous limbs, because those are the first. So we can pre-generate these and have them forever, and all the attacks we can use them. So we now know how to start and how to proceed. We can recover the entire key. And I can see you're tired, so for a change of pace, we're just going to chat about kangaroos now. Aren't they cute? But we're actually going to use kangaroos to finish the attack. So we're going to use the polar kangaroo attack to find the last bits of the key. We could just run the oracle until the end, but this makes it much faster and, more importantly, allows us to find the result offline. It's optional, but it's fun to learn about. It's also fun because now I had an Australian dispute this, but Pollard in a cryptography paper maintains that this is true, and I'm not arguing with Pollard. So apparently, kangaroos jump based on the ground under their feet in the point where they're jumping from. So if you put 2 kangaroos in the same spot, they will jump in the same direction and at the same distance. How do you use this? Because, well, what if you have to catch kangaroos? You had some times to catch a kangaroo, right? That's annoying. So what you do is that you take a tame kangaroo, which of course you have laying around because you have a tame kangaroo, and you put a GPS tracker on it, and you let it loose. It jumps a lot, it makes a lot of footprints, and eventually you go pick it up. It made a lot of jumps, and you go pick it up, the kangaroo. And in place of the kangaroo where you found it, you put a trap right there. Then a wild kangaroo is hopping around. Now, it's very unlikely that the wild kangaroo will step into the trap, right? But it's more likely that we'll step into the footprints of the tame kangaroo, because it left a lot of those. And we know that if it steps in the same spot, it will keep jumping the same way from there on. And so eventually it will end up in the trap. So this is how you catch kangaroos. And that was it. That was the end of the talk. Like, that's it. But if you really want to use it for elliptic curve cryptography, you just have to define how a jump is defined in an elliptic curve. Now, we can define it by taking a point, hashing it, and adding it to itself. This operation, qn plus 1, will depend only on qn. So it has that property of the kangaroo jump, that it only depends on the starting point. The next step depends on the starting point of the point. A lot of points. So we use this to catch kangaroos by, to find private keys by taking a tame point. A tame point is one we know the private key of. And we make it do a lot of jumps. And then we only save the final position. We don't save all the intermediate states. We save the final position and how much distance the private key has traveled effectively to get there. And then we take the point we don't know the private key of, and we run it a bunch. We do the same thing. We hope that it will intersect at some point with the chain that the tame one did. And if it does, it will end up in the trap by ending up exactly the same as the chain that we started from a known point. Since we know where the chain ends, and we know how far the wild point traveled, we can backtrack, and we find the private key. Now, this is actually a valid algorithm to find private keys for full-fledged attacks. But of course, you can't apply it against a 256-bit key because, again, heat death of the universe, yada, yada. But the advantage of this attack is that if you know that the private key lies in a range, it's as if you knew that the wild kangaroo is in an area. And if too much time passes, it probably escaped, and you can start over. So this is useful when you know that the private key lies in a range. And we know that the private key lies in a range when we know a bunch of limbs already, and we just don't know how the number finishes. It will have to be between the known limbs and 0, and the known limbs at 32. So that's a range, and this is a more efficient attack. I swear I didn't make this up, and it comes from the same paper from which the raw attack comes, which is the attack to find private keys. So now that we know how to start, how to proceed, and how to end, we just need a target. Now, as I told you, you only use elliptic curve Diffie-Hellman in ephemeral static way, where the one private key is fixed, if you're extremely brave. And we know that usually cryptographers shouldn't be brave, but we also know that sometimes programmers come and they're like, man, I want more choice. I want to be able to use any primitive I want, and I want to be able to combine them however I want, and I want to have to choose them, and I don't want you to give me any guidance about which ones to use, because I'm a mature adult programmer and I'm going to use what I want. So Josie was built based on that understanding, and it allows you to use anything, including elliptic curve Diffie-Hellman in ephemeral static mode. Now, if you couldn't tell, I was sarcastic, and friends don't let friends use Josie and JWTs. But people still use them. So, we just find ourselves a off-the-shelf Go implementation. This is no fault of their own. And we check that it does support elliptic curve Diffie-Hellman in ephemeral static way, because of course it does. And we build it with a vulnerable version of Go, maybe the last one before the patch was applied. And we build a small service, something that publishes its public key and accepts encrypted messages. And there will be either a timing difference or an error difference between this does not decrypt and this decrypts, but I don't know what you sent me. So that's our oracle. This does not decrypt, triggered the bug. This decrypts, but I don't know what's in it, did not trigger the bug. And we just use that to build our adaptive attack, and we recover the entire key. We actually built this, and we built this with an infrastructure where there's a small dispatcher program running on a laptop or anything, maybe with ngrok exposed. It runs a HTTP server with 2 endpoints. Work, which allows a pool of workers to ask, okay, what should I fuzz next? And Then result, which is for when, hey, I found a useful point. Here is it. It has a short timeout, so if someone else finds if you find the limb and you want to move on to the next limb, all the workers will check in soon to figure out more work. And the workers can be anything. They can be cloud instances, pod instances, preemptible instances, botnet instances, whatever you like. They just have to be able to connect to an HTTP endpoint, ask for work, and do some work. So this scales horizontally as much as you want. And it allowed us to do the attack from top to bottom for a full recovery of the key. So here are some numbers. For each key, there are 52 limbs, ignoring the kangaroos. For each limb, you will need on average 16 points before you strike the right one. And each point requires about 2 to the 26 tries to find a candidate point. So about every limb is 85 CPU hours, which clocks the entire attack at less than 5,000 CPU hours, which you can buy from the cloud for less than $50. So you can run the attack, and it will take about 800 and spare queries to the Oracle, less if you have a lot of kangaroos, and $50 in offline computation, and you will have the key. So now we're going to have a live demo in which I'm going to attack a live running server from the conference Wi-Fi. No, of course I'm kidding. I am not that brave. Instead, we're going to have a recording of exactly that happening. This is a UI built by Sean where you can see each remaining candidate for the next limb. And in red, all the candidates that we found a point for, and we sent it, and it was not the right one. And in green, the ones that we sent, and it did cause the bug, so we know that that's the limb.
Is this sped up at all?
It's sped up, yes, I'm cheating. As I said, not that brave. And also, you don't have the time to stay here and see it run. But what's beautiful about this specifically sped up is that you know how those Hollywood movies that depict hacking in all the wrong ways, and there are these people with these UIs where the numbers spin very fast, and then it finds one and moves to the next one, and then it finds that and moves to the next one, and we're all like, that's absolutely bullshit. That's not how any of that works. It is. It is. It really is. I love this. The reason cryptographers get into adaptive attacks, it's not the papers. It's that you can build these UIs. Look at the key at the bottom, slowly being stopped. Yay! Look at the key at the bottom, slowly rolling and appearing more and more as more bits are figured out. So yes, this is beautiful. Now, we could stay here, stare at the demo for a little while. I love it. You probably don't. So moving on. What?
How long did this really take?
So in real time, this really depends on how many workers you have, which depends on how brave you are, because you have to decide on one side, it will make it faster and save me time from my life. On the other side, if I forget to turn them off, that's going to cost me a fortune. So this one took a few hours, I think 12. With double the workers, it would have taken 6. With double, it would probably have taken down by someone thinking it was mining Bitcoins. So now, as I told you when we started, I was not at Google at the time. I am now at Google. I'm now on the Go team, and I now own the cryptography libraries in the Go project. So now this is my problem. So here's the new policy on what you need to do before we will accept your assembly from now on. And you know, it's pretty obvious stuff like we prefer Go, so if we can make the compiler faster for you, tell us and write Go that is easier to review. Because let's acknowledge it, assembly is hard to write and it's hard to review. And then if you have to write assembly, tell us why, and then test it well, test it into small chunks, because this function tested individually was easy to detect, but tested in the whole, it would have taken forever. And connected to, give us fuzzing hooks so that we can fuzz everything. And we're in the process of cleaning this up. So hopefully this does not happen again. Now, in closing, if you liked this talk, You probably also like the CryptoPals, the crypto challenges I told you at the beginning. And here's a treat. If you followed this talk, you have a head start for the latest CryptoPal set written by Sean, literally on the plane over here, dropping hot off the press, dropping right now if SSH was working. So that's the URL. And finally, everybody took a picture. I'm going to wait for you. Yes, you. Yes, no stress. Don't worry. No, don't worry. Yes, we're just all waiting for you. But in closing, thank you very much. And as Uma Thurman said in Kill Bill, leave the limbs you lost. Those belong to me and Sean now. And thank you very much.